Saxon Advanced Mathematics Lesson 3. You guys, are you ready for some fun? I know I am. We're going to talk about Pythagorean Theorem today. Review some properties with that. Remember what it's good for. And then we're going to talk about similarity. What makes objects similar, geometric shapes similar, and in particular we're going to talk about similar triangles. Okay, so it's kind of two topics. Let's dive into Pythagorean first and review that. Remember that the Pythagorean theorem works with right triangles. It has to be a right triangle in order for the Pythagorean theorem to work. And when we use this, we define A and B as the legs of the triangle. It doesn't matter which one is A and which one is B, but it matters very much that A and B are the two legs, which are the straight edges, and then C is what we call the hypotenuse. And that's the side that is opposite the right angle, and it's the, to me it always looks like a piece of paper that's been cut on the diagonal. So that's how I always think of it. And we can use this equation, which is the Pythagorean theorem, to solve for missing sides on the triangle. It works in squares, so the calculations can sometimes get a little kooky, but that's okay. We can leave our answers in square roots, and that's fine. All right, that is a tool that is super useful. Remember, Pythagoras was this dude who lived on a Greek isle and figured all this out. He lived in the 6th century BC. He was born in the Aegean island of Samos. I think it's a Greek island. And was later associated with a school or brotherhood in the town of Crotona on the Italian peninsula. So, long time ago, you guys, almost 3,000 years ago, 6th century BC. Yeah, that's a long time ago. 2,600 years. So, he's alive and well today. Just think, he was like an actual person who walked the earth and ate pickles and probably threw stones in the ocean. And he came up with this fabulous idea that we are still in love with to this day. So that's pretty cool. Here is something that's fun that we can do if this is true when c squared equals a squared plus b squared. We know that we have a right triangle, right? And that's kind of the opposite of what I just said, which is that it has to be a right triangle in order for this to work. So this we know, that's obvious. But sometimes we can draw information from inequalities regarding these same numbers, the same information. If we take the longest measure of a triangle and compare it to the two shorter sides, and this one is bigger, then we know that we have an obtuse triangle. Triangle, and remember that's where one of the angles is greater than 90 degrees. This is a picture of an obtuse triangle. It's a little sloppy. And that makes sense, doesn't it? Because we can see, okay, that long side is way longer than the two shorter sides. So it would make sense that this would be true. Conversely, if we take the longest side and we square it and compare it to the other two and find that it's smaller, then this tells us that we have an acute triangle. Acute triangle is where all the angles are less than 90 degrees, okay? So this is information that we refer to as Pythagorean inequalities. this is a good thing to write. All of this, actually, that we've covered so far is worthy of being written. I think we talked about this last week, but I'll remind you, in your notebook that you use for your homework, which ideally should be the same notebook you use for your notes. Put it all in one notebook. It's easier to just keep everything together. This cover doesn't work because it's plastic, but my back cover is ideal. I can write my notes about formulas and things that I want to remember right down there. And then when I'm doing my homework, if I need to reference something, I can just flip a few pages and there are all of my notes with all this information at the ready. Please use this tool to organize your formulas and get everything the way you want it. At the beginning of the year, what I like to do is we'll just add as we go. You don't have to sit there and try and remember all the formulas you've ever learned in math in your life. I mean, you can if you want, but we don't have to make it that hard. We can just add them as we go. But then when you fill up one notebook full of homework, we'll have you copy all of the data into the next one. It's a great way to help yourself memorize. It's all there if you need it. Please use that reference wisely. I have tried a lot of different strategies for helping students keep track of formulas over the years, and this back of the book thing is by far the easiest because it's right there when you need it. Okay, so all of this is back of the book worthy, and like I said, if you want, just pause me right now before we go on and get all of this organized back there. Okay, if you're back, then let's go ahead and try the first example. It says the lengths of the sides of a triangle are 7, 5, and 4 respectively. Is the triangle a right triangle, an acute triangle, or an obtuse triangle? We're supposed to figure that out. Now, we could try drawing a picture and using a ruler, but we can use this simple inequalities test to make it work. This will be our C because it's the longest of the three sides. And then we'll make this our A and our B. That doesn't matter as much. Remember, they're the quote-unquote legs. And in these formulas, we're going to square them and add them together so it doesn't matter which is which. So the first thing we have to do is square all these and put it into this format. So C squared is 49. And then we don't know what symbol we'll have. And then we'll have 5 squared. 5 squared is 25, plus 4 squared is 16. So then that becomes 49 compared to, this is 41. 49 is greater than 41. So then we look up here and we see, okay, that tells us this is an obtuse triangle. And that's correct. Easy, right? All we're doing is just using these inequalities to test a particular triangle and see which category it fits into. So that's an example of the first one. Okay, enough about Pythagoras. He's back on his island. Let's talk about similar polygons. And I'm just going to show you the book because I don't want to copy all of this. I know there's a big shadow. I hope you can see well enough. Polygons are simple, closed, coplanar geometric figures. Okay, simple means their lines don't cross over. This is not a polygon, nor is this, because their lines cross over. Closed. This one is not closed. It's got an open edge, so this is not a polygon. Coplanar means that they are not three-dimensional, they're two-dimensional, they're flat, and we can't really draw effectively a non-coplanar geometric figure. So just keep that in mind. They don't go three-dimensional. This one's got a curved edge, and polygons always have straight edges, okay? If it's got a curved edge, like this little ice cream cone, then they're kind of hybrids and not true polygons. All right, these are all polygons. It's okay to have a cave. Here we have different straight sides. This one's equilateral, meaning that the sides are all the same length. This one's equiangular, meaning that the angles are all the same length, same size. All right, this one's called a concave. Any polygon that doesn't have a cave is called a convex. All right, here's a concave. And John makes this point that you can, any 2 points on the interior of a convex polygon can be connected with a line segment that stays inside the polygon. Okay, so these guys are convex, and any one of these points drawn to any other point is going to create a line that stays within the body of the shape. That makes it a convex. This guy's a concave because there is a way to draw points that go outside of the polygon and then come back in. I mean, sure, right? Informally, we say that 2 polygons are similar if each is a magnification or a reduction of the other, because they have the property of sameness of shape. Okay, that's a lot of words. This is how I think of it. John wrote this before the advent of personal computers as we know them now. They used to be called personal computers. Now they're just computers. But the whole click and drag idea, right? When you click on the corner and pull a shape on any kind of imaging program, it creates the same shape, only bigger, or you can make it smaller. That's what similarity is it's click and drag. And what it means in geometric terms, 2 objects are similar if the angles are the same from shape to shape, but the length of the sides is different. Okay, this is the definition of the word similar in geometric terms, and it kind of makes sense because in general English, similar means things are kind of alike but not exactly, right? And let's just draw an example. Here are 2 triangles. One's clearly bigger than the other. But if I label this angle as being 130 degrees and this angle as being 30 degrees, and then do the same here, we know for a fact that these must be similar in the technical sense of the word because corresponding angles are correspondingly the same size, right? It's not all angles are the same size. I should be clearer on that. But you know what I mean. Corresponding angles match. What about this one? We don't know if these match. Oh, but wait, we have 2 out of the 3. So we know that this must be 20 degrees, right? Because they have to add up to 180. And this one must be 20 degrees also. So we can see that the lengths of the sides are quite different, but the measure of the angles is the same. Okay, yay. What can we do with this vast knowledge of ours? We can solve problems. Here comes a picture. These are fun to draw. These are like bow tie pasta. You know what I'm talking about? It's 2 triangles hooked together. Pretend it's perfect. And what's weird about these pictures is that they're kind of twisted. So in order to understand the way the picture works, you kind of have to mentally twist them. First, I'm going to draw what John has in the book, and I invite you to draw with me. Okay, and then we pay careful attention to the marks. Oh, I'm sorry, I'm copying from the wrong problem. This should be like this. That should have a single. No, this one's a double. This one's a double. And then these are singles. Okay, and it says find X and Y. Okay, so there's the X and there's the Y. All right, the first thing that I like to do is redraw the triangles so that they are like this, so that they match in the way that they're laid out. So I always draw the first one the same as the picture has it, the one on the left. So this is 4, this is 5, this is X, this is the single dashy, this is the double dashy, if I can quote Mario. Now I'm going to draw another triangle that looks like it more or less, but is bigger. I'm going to put the doubles up there and the single down there, right? So now these two correspond. Now I have to relabel it and keep my orientation straight. So here's the side between the single and the double mark. That is 7. So here's the single and the double, and that is 7. See how I used these marks to orient myself? The far end is Y, and then 6 is along here. Okay? This might be the hardest part of the problem, is getting the diagrams oriented properly. All right? Now I've taken this picture and I've turned it into something that I can compare more readily. Right? I can find corresponding sides really easily. The nice thing about similar triangles is that the length of their sides might not be the same, but they are proportional. So we can use proportions to solve. John also uses something called scale factors, which you guys have seen in the past. I don't like scale factors. I think they're needlessly complicated. I prefer to just use proportions. So I'll show you how it works. You'll always get the same answer. It's just approaching the algebra a little bit differently. So the first thing we do is we look for what's called our anchor proportion. The anchor proportion is simply proportion. I spelled it wrong, sorry. Is simply the pair of sides between the two triangles where they each have a number given. And I can see, okay, the 4 and the Y, that's not going to work. The X and the 6, that's not going to work. But the 5 and the 7 are both numbers. So 5 over 7 with the left triangle on the top and the right triangle on the bottom, that's going to be my anchor. To solve for X, let's go in order. I'm going to take those two pair of sides and set them equal to it. Okay, so left and right, left and right. I've created an equation that is consistent. I have the information about the left triangle on top, and I have information about the right triangle on the bottom, the triangle on the right. And I've got the pairs matching. Okay, this is, again, it's not hard, but you just have to pay attention to the detail here. Now I can solve for X. I'm going to cross multiply and get 5 times 6 is 30 equals 7x. And then I'm going to divide both sides by 7. And I'm going to get x equals 30 over 7 units long. That is wildly dissatisfying in terms of a number, but that's the right answer. And then to solve for y, we're going to use the same anchor proportion, 5 over 7. And then this time we'll take the information about the pair of sides that includes y. Y is this one, so it'll be 4 over y. Taking care to get the right things in the right place, right? This is the 5 and 4 are on top. 7 and y are on the bottom. The 5 corresponds with the 7, and the 4 corresponds with the y. Okay, got it. Now I cross multiply, and I get 28 equals 5y. Remember when you're cross multiplying, you can go this way first, or you can go that way first. I've mixed it up, right? First I did 30. I went top down to get the 30, and then I did the 7x. This time I did it in the opposite order. I did this way first. I did the 28 equals 5y second. It doesn't matter. For some reason, I just like to have my variable on the right-hand side. It doesn't matter. That's just my go-to style. Divide both sides by 5, and we get y equals 28 over 5. And that is also the correct answer. Remember, this is called the proportion method. If you like to use the scale factor method, you are more than welcome to. When we get a little further in, I will review how that method works. But right now, I just want to focus on the proportion method and let you get comfortable with that. Okay. Moving on, example 3.3. Find x, y, and z. Okay. Get to draw another picture, more bow tie macaroni. Notice the way I drew that was I put in these sides first and then I drew the x. I try to make them parallel. I make one short and one long. And the pictures usually turn out decent. Okay. My picture doesn't look like that's a perfect right angle, but by putting that symbol in, I can convey that information accurately. X, Y, 7, 10, 8, Z. This is how I make my Z's. I put the hash through it. That confuses some people because some people put the hash through the 7, but I put a hash through my Z. So now you know. Okay. Find X, Y, and Z. All right, we can do that. What I prefer to do again is redraw these triangles. I keep the first one oriented the way that it already is. Y, X, and Z. And then I draw another one like it. I got kind of carried away with this one, didn't I? Okay. So I'm flipping it. This is the 8, this is the Z, and the 10's down here. That one is a little harder to do because I don't have as many reference points. I just have this one. But I took it and I flipped it to put this at the top, and that's how I visually figured out where those should go. Okay, again, I'm going to use the proportion method. John is using it too. I find my anchor proportion first. That's where the pair of numbers is. It's the 7 and the 10, right? So 7 over 10 is my anchor. First, I'll solve for x. Okay. X goes on the top, and then 8 is what corresponds with it. Just a second, I feel like I've... Eight. John has 8 corresponding with y, and I'm trying to see. Oh yeah, I drew my picture wrong. Because this angle and this angle, these correspond. So this angle is here, right? And that means I have to rotate this as well as flip it. So this one has to be over here. And then the 8 is between those two marks. And the Z is over here. Okay? So the moral of this story is if there aren't enough marks on the triangles to make sense to you, add some. I needed to add these in order to see how to do it correctly. So now I see that the X corresponds with the Z. And that gives me a headache because I can't solve 2 variables with one anchor proportion. So instead I'm going to solve for Y. 7 over 10 equals Y over 8, right? 7 over 10, Y over 8. Beautiful. This one has 2 variables, so it's not going to work as is, right? But once I get my Y, let's see what happens. I'll cross multiply. I'll go down first. 56 equals 10y. Divide by 10. That gives us 56 over 10. which is equal to, what John does is he goes to decimal land. I mean, okay, I'll do it the way that he does it, but normally mathematicians always prefer fractions. No, I'm gonna leave it in fraction form. I don't wanna do it in decimals. That's how John's doing it, but you know what, that's his problem. So this I'm going to reduce to y equals, it's what, 28 over 5. I just reduced that fraction in my head. That cancels. All right? Y equals 28 over 5 or 5.6, right? If we just decimalize that. Okay, now I've got my value for y. Okay, now we want to do something to solve for this one. And what we can do is go back to this triangle and say, okay, is there another way we could solve for z? And there is, because this is a right triangle. So to solve for z, that's an O, we can do okay, so here we're going to solve for y, and we get it, and that's correct, by the way. Now we're going to solve for z, and we're going to use not the proportion method because that doesn't work for us. Scale factor won't either, too many variables, but we can use Pythagorean. We can see that z squared plus 8 squared should equal 10 squared. This is what allows us to use Pythagorean because we know these are right triangles. Okay, so z squared plus 64 equals 100. I'll subtract 64 from both sides. Oh, that's an underline. Z squared equals 36. So z equals 6 units. Yay. I like that. Okay, so we use Pythagorean to fill this in because we had 2 of the 3 legs. Now we can go back and solve for x because we have a number here. So to solve for z, I'm sorry, for x, we can do our anchor proportion equals x. We calculated that was equal to 6. So x goes over 6. And that gives us 42 equals 10x. We can divide by 10. So then we can say x equals 21 over 5, or the way John does it is 4.2. And is that the correct answer? Yes, that's the correct answer. Yay. Okay, so this gives us practice not only in using that anchor proportion, but also in tossing in Pythagorean a little bit to solve. Again, remember, we needed to know that they were right triangles in order to do that. All right, moving on. Example 3.4. Oh, this is a classic. In example 3.4, we are given a diagram that you will see many times in your advanced mathematics career. I'm copying it out of the book. There's the shape. Now I'm ready for the numbers and the letters. We have 3 variables, A, B, and C, and then we have 6 numbers. Okay? That's a lot of information on a complicated looking picture. What are we going to do? I'll tell you what we're going to do. We're going to peel these apart. Imagine them as transparent stickers that are layered over the top of each other, and we're going to peel this bottom triangle off, and set it over here. Right, so I'm copying all the information for this bottom sticker. Now, underneath it, we have the bigger one. My drawing's a little scribbly today. Okay, it looks like this. Notice they have the same toe, right? Because they were on top of each other. Now we have to get a little bit creative in coming up with these sides. This one, along the bottom here, we can see is 10, because we add those two together. This back end we see is C. But the hypotenuse is the tricky part. We have to write it as A plus B. Okay, so we added this side and we add that side to get the larger triangle. All right, so how the heck are we gonna solve this? Well, we look around for, there's an anchor proportion. We could use that to solve this, but let's try to get A figured out first. And we see, oh, we've got 2 out of 3, so we can use Pythagorean. Okay, so that's going to be our first step. We can't use proportion method to find A, because even though we have an anchor proportion, which would be 6/10, this would be A over A plus B. That's not going to work. Again, let me give you the hint that very often with these problems, if you solve for the variables in alphabetical order, or the order that John lists them, which he does say find A, B, and C, it usually flows nicely. So we're going to use Pythagorean to find A. So A is the hypotenuse, so we can say that 4 squared plus 6 squared equals A squared. Right? Those are the 2 legs. It doesn't matter which order they're in. So this is 16 plus 36 equals A squared. And that is what, 52? Equals A squared. And that means A equals the square root of 52. Can we simplify this? Let's do a quick little prime factor thing here. 52 is 4 times 13, right? And then 4 breaks down into 2 plus 2. So just to catch my new students up on the way I talk about these things, I referenced the story of the 3 little pigs. This is a pig house. There are 3 pigs inside this house. There's a 13, a 2, and a 2. A pair of pigs can come out, but a single pig has to stay in. So we can rewrite this as A equals 2 to the square root of 13, right? If it's a pair of pigs, pair of matching pigs, they can come out. All right, so there we have our value for A, and that is correct. All right, now we've got some information. We now know that this is 2 times the square root of 13 plus B, and we know that this is 2 to the square root of 13. Okay. Now we're ready to solve proportions. Let's go ahead and do B next. Ready? It's going to be a little crazy, but that's okay. Our anchor proportion is 6 and 10. 6/10 equals, ready? 2 square root of 13 over 2 square root of 13 plus B. Well, that does not look like my idea of a good time, but it'll work. All right? So here we go. We cross multiply. That's my symbol for cross multiplying. I haven't been using that, but there it is. I'm going to put parentheses around this to remind me to distribute, right? So I'll write it out I'm going to do it on the next page. I'll write it all out so that you can see exactly what I'm doing. 6 times 2 square root of 13 plus b equals 10 times 2 square root of 13. All right. I didn't do any of the actual multiplication yet. I'm just showing you. Those are the cross multiplication pieces. Okay. So that's how I designate cross distribution so that I remember to catch both pieces. So I get 12 square root of 13 plus 6b equals 20 square root of 13. Remember that the rules for multiplying by radicals is that we multiply wolves, which are the numbers on the outside of the houses, and those are pigs, right? These are wolves, these are pigs. We multiply wolves times wolves and pigs times pigs. In this case, we only have we're multiplying by wolves, right? There's no pigs in houses attached to those numbers. So we multiply 6 times 2, that's wolf times wolf. Pigs come along for the ride. And then over here, wolf times wolf, and there's the pigs. Okay. Basic algebra. Do a little subtracting. 6b equals 8 square root of 13. And then divide by 6. That cancels, and we get b equals, these wolves can simplify, 4 square root of 13 over 6. That is by no means a satisfying answer, but it's right. Okay, and then we have to figure out c as well. Flipping back to look at my picture. C is going to be easy though because we can use our anchor proportion and then 4 over c. So 6 over 10 equals 4 over c. So we're going to use our anchor to find c. What was it? 6 over 10 equals 4 over c, right? Yes. And that is 6c equals 40. Divide by 6 and reduce. C equals 20 over 3. Yay. Ooh, those are crazy eyes. This problem does not have neat, clean answers, but we did it. And the last problem for this lesson, yes, we are almost done, is another super classic shape. That one, the problem we just did where it looks like this, that is a shape that shows up again and again and again in geometry, and this one does as well. This one's a little bit more challenging to draw, but it's super fun once you get the hang of it. This is actually 3 triangles. There's the big one on the outside. And then this time we layer 2 triangles on top of it. Here's a little one, like this. And then here is a medium size, like this. So we have large, medium, and small. And what's cool about them is that they're all similar. So I'll show you how we're going to draw them all separately. This time we're going to start with the biggest one first. I don't like the way I drew that. Okay, so there's the first one. And it's got this there, this there. Then we're going to draw the medium-sized one. And then we're going to draw the little one. Okay, they all need to have this there. Oh, I didn't put the numbers on it yet. That would help a lot, wouldn't it? Let me finish. Let me stop drawing. Ignore that line, PS. Let me go back and put letters on. This is A, this is H, this is B. Okay, I see a lot of letters and I see a lot of numbers. Now, one thing that's helpful is that the convention in geometry is to use uppercase letters to denote the angles and lowercase letters to denote the sides. So we're going to use that to help us keep our heads on straight. So let's go back now and put letters on this first one. Remember, we're using this outside triangle, the whole shape. So this is M and this is K. This long side then would be 4 plus 8 or 12. This, between angle 1 with the tick mark 1, the single tick and the right angle, that's side A. And then this is side B. Okay, now we're going to the middle-sized triangle. This is the right angle here, so we're flipping that up. This has the 2. Okay, so this is angle K. This long side is B. This side is 8, and this is H. Okay, and then this is the little baby. There's the right angle. So in order to get this oriented right, the shorter side is the 4. The straighter edge is the H, right? 4 and H, and then the hypotenuse is the A. On this one, the hypotenuse is the B, H and 8. Okay, I think I've got everything in the right place. All right, so you see what I did. I took the, let's see, this is the single. I took the original diagram and I split it into 3 diagrams that are all oriented the same way. That will help me find my anchor proportions and figure out the pairs. The letters of the angles are just there to help me get my orientation straight. All right, and again, breaking the original triangle into the separate triangles is probably the hardest part because it's so easy to get turned around. This is a great place to stop and check your work in the solutions manual to make sure you've got these diagrams drawn correctly. And just so you know, I'm always doing that as well. I'm comparing it back to the book as I talk to make sure I didn't mess it up. All right, so what I'm gonna do is I'm gonna look for some anchor proportions between the triangles. Or if I can't find an anchor proportion, if I can find the same letter, that will work. So for example, let's look at the A's because I'd like to solve that first. I see A over, I could compare A to H. That's not helpful. I can compare A to 4. Okay, that's really helpful. But if I find a corresponding pair of sides between the 2 triangles, look at that. I can go A over 4 equals 12 over A. Okay, I'm trying to solve for A here. Okay, that's helpful because even though I have 2 variables, it's the same letter. So that's going to solve quite nicely. I can multiply it and say A squared equals 48. Take the square root of both sides and I get A equals, let's see, can I break this apart? That's 4 times 12. Right? This becomes 2 and 2. And this is 2, 2, and 3. So I can pull that apart. I can take out 2 pairs of 2's, and that becomes 4 square root of, that's what's left, 3. 3 is the only pig left. All right. Now I'm taking square roots. Does that mean I need to consider the negative of this value as well? No, because in geometry, we can often rule out the negative root. There's no way that the length of that side is negative 4 square root of 3. That makes no sense. So I can disregard the negative roots. All right, A, 4 square root of 3, yay! Okay. How about B? Is there a way we can find to do B? Let's look where B is. B, okay, if I go down here to this other triangle like we did last time, I get an H. That's not gonna work. But what if I do B over 8 as one of my proportions? And then 12 over B. That will work just like this one did, right? So I can go B over 8 equals 12 over B. And that works exactly like this one, right? Where I'm gonna get a square. I'm gonna get B squared equals 96. And then I'll take the square root of both sides. And 96 is gonna break down a lot for me, isn't it? It's going to be, well, let's see, I know it's 8 times 12, so that's gonna be 2 times 2 times 2 times 2 times 2 times 3, right? Because 8 is this and 12 is that. And I know that's what I multiplied together to get that, so I can use those two to help break it down. Okay, so what that means is that I can take out 2 pairs of pigs. That gives me a 4 as a wolf, right? Because I multiply the individual of each of those. And then I have 6 left on the inside. Again, I can disregard the negative root. Yay. And now I need to find H. And I will use, can I use the same strategy? Yes. To find H, I'm going to use H over 4 equals 8 over H. Right? H over 4 equals 8 over H. So what I want you to take away is that when we're doing 3 triangles, we have a lot more options about the way we compare the sides. And because of the way this diagram is set up, we'll always get this pattern where we can find the same letter on 2 different triangles and then work it in the same equation. We'll get a square that way, but that's okay. We know how to deal with those. Okay, now I just need to do this one. H squared equals 32, square root of both sides. This is 2 times 2 times 2, that's the 8. Times 2 times 2, that's the 4. Pair of pigs, H equals 4 square root of 2 is the only pig left. Okay, and so there's my third and final answer. Yay. All right, that is the end of the lesson. You'll see that in the practice, or the problem set rather. I'm pretty sure, if I remember correctly, this book doesn't have practice. Yeah, it always goes straight to the problem set. So you never have to deal with practice problems. You'll find new material just dropped into the middle of the problem set. So you'll see we have some where the triangles are drawn separately. We have some twisted macaroni. We have this one, and we have this 3-in-1. All right? So take your time at the front end of those problems to make sure you are spatially understanding what's going on, right? That you're twisting and turning these triangles all over and getting them to match up. That will help you quite a bit in getting the sides, the pictures drawn properly so you can match up the correct sides and create the nice proportions. All right? That is the end of lesson 3. Let me just give you a recap on how we'll be doing the homework this week. Today is the first day of your week, and you just watched the first lesson. Okay, so you watched lesson 3. Today I want you to do the odds, Tomorrow I want you to do the evens. Then I'll have you watch lesson 4 and do the same thing. Okay? This is our second week of working this way. It'll be our last week of working this way. Then we'll accelerate up to 4 lessons a week and go from there. Okay? So that's all for today. I will see you in a couple days and talk to you about lesson 4. Yay, bye.